Hello again. This is Math 2245 coming to you from the College of DuPage. And the title of this lecture is a footnote, and it's a clarification of a discussion that we had in proving a theorem last night. And as always, please be an attentive learner while watching this video. Okay, and a student asked a question during the midst of a proof, and my answer was sort of summarized, that's the way inner products work. But another good student after class stopped by, and we chatted for a while, and again, my summary answer is, that's the way inner products work. The goal of this video is to give a better, more complete answer. So we were doing theorem 3 here, and we were showing that this is true. So if you have an orthogonal matrix, it preserves lengths. That is, the norm of Qx is the same as the norm of x for all x and Rn, and it's norm preserving. And the proof was going like this, and this is the step that caused some challenges. It says we know that we can write a dot product as, and then it doesn't really give you much detail, but it says the norm of Qx is equal to, and it is x dot Q transpose Qx all to the 1/2. And that was the point where people said, where did the Q transpose come from and what's really going on? So my goal is to answer that question more completely than saying that's the way inner products work. And it's always a good thing to talk about an example, and the example I think will make the general case clearer. So here what I'm doing is I am taking a matrix. I'm not calling it Q, I'm calling it A, but this is orthogonal. That means that it is the columns are orthonormal vectors. And the theorem said, or at least we previously had proved, that gee, if you have such an A that is orthogonal, its transpose, and this is the transpose of A, is its inverse. And you can see if we multiply these together, we get this. So that is what we expect. And in fact, that being equivalent to being orthogonal, that means this A is in fact an orthogonal matrix. And then, just as an example, I'm going to say, well, let's test our little idea about it preserving norms. So I'm going to say, what happens when I take A times X? Now, this is not a general X, but I'm taking a specific X. This is 1, 2, 3. But if I multiply these two things together, I get this. Okay, now this is a key point though, because I could say, okay, so I could just take the dot product of this with itself, and that would be the norm of AX squared. But you can do that as a dot product, but you can also view that as a matrix multiplication. But if you view the dot product as a matrix multiplication, you have to take this and do the transpose. So you see I'm taking this vector AX, but I'm multiplying in the front by the transpose. Now this is the dot product, but now I've changed this from a dot product to matrix multiplication. Now I still get the same answer. I still get 14. And then it would be the square root of 14 would be the norm. But notice that I changed it from a dot product of a column dotted with a column to matrix multiplication of the transpose of the column times the column matrix. And just to show that this theorem is true, this is what AX dotted with AX is squared. And if I take X dotted with X in the same way, I get the same answer. So the theorem is true in this example, and this provides some real insight into the way the theorem works. Okay, so here was the problem again, and we were trying to do this step here. Now, I think this is more clearly explained in another, because there's kind of some steps taken here, and again, the author just said, oh, we know this is true. Let's talk more detail about that. Now, here's more or less the same theorem, and this is proving these things in a little bit different order, but I'm going to start with QU dotted with QV here. So QU dotted with QV, so what I'm doing is I'm showing that B implies C, so C is true. Then I'm going to use C to prove D is true. So let's continue with this. Okay, so so here we go. So what I'm going to do is I'm going to assume that V is true, so it's Q inverse is equal to the transpose, which it is for an orthogonal matrix. Okay, so now what we're going to do is we're going to do this calculation here for C. So QU dotted with QV. Now, in the same way I did in my example, I'm changing dot multiplication of vectors to matrix multiplication. So you see, when I'm doing that, this is a column vector times a column vector. So I'm going to change it to a row matrix times a column matrix. Now it's the same thing, except instead of having a column, I have a row, so that is where the QU transpose comes from. Now I'm going to use my properties of transposes to say that QU transpose is U transpose times Q transpose. That's a property that we know. And then it is QV. Now I'm still doing matrix multiplication, but now I use the associative property. Associating these, I get the identity matrix. So then this is going to be U transpose times V, because that's the identity matrix. But U transpose V is U dot V. So you see what we're really doing is we're changing the dot multiplication to matrix multiplication and back again. So what we've proven is that the norm of QU, or the inner product of QU with QV, is the same as U dot V. But we went through the matrix multiplication to do that. Okay, so we've proven that if something is invertible, that is Q inverse is Q transpose, then this is true. And D, the thing that we were really trying to prove, comes very quickly, because you see, if we know that this statement is true, I just can pick V to be U. So I get QU dotted with QU is U dot U. And so this follows. That was helpful. In closing, now more than ever, time is precious. Each day must count. Do the math, it'll make you strong. And now more than ever, take care of yourself, because self-care is important, and of each other, because we're all in this together. God bless you all.